No, what we'll go through and do is show the work. Okay, I didn't ask for the work, but that's the part of this. So, one thing, we went through this, ow.
You okay with your tongue?
Yeah. We went through this really fast last Wednesday, right? And rewatching the video is a good idea, but because I went through it really fast, if you just watch the whole video all the way through, that's going to become difficult. So watch the whole video for a step and be like, stop! Now let me work a problem. Okay, I think I'm good, let's move forward a little bit. Stop! Now I'll add a little bit more information. So take advantage of that pause feature within the video to go through and slow it down to a level that works better for you. All right, so with this one, we want to split into the half reactions. What I'm noticing is that I've got aluminum going to aluminum and copper to copper. So I'll go ahead and split these into the half reactions. Aluminum to aluminum plus 3. I'm going to just start with that one. Is that one balanced? No. What's not balanced about that? They have aluminum. The charge isn't balanced. To balance the charge in the half reactions, we're allowed to show electrons. In fact, it is a requirement to show the electrons. Right? So I'm going to say, I'm going to add an electron. Here we go. 1 electron. Don't write in pen, by the way, just for the record. Okay? What happened to the charge?
It came down by 1.
The charge on the left-hand side is now -1, right? And the charge on the right-hand side is? Still plus 3. Did I get closer or further from the charge balancing?
Should be positive 1.
It's not positive 1. The aluminum on the left-hand side is a 0 plus an electron. The electron charge is -1. So our total charge on the reactant side is -1. Did I get closer or further?
Further.
Okay. We went further. We started at 0 to 3, and now we're -1 to 3. So we are now further from our balancing, which means what?
We're doing it on the wrong side.
Mike was a horrible guesser. He placed the electron on the wrong side. This is why I said don't use pen. Let's place the electron on the other side. Now what happens? On the left-hand side, I have a 0. On the right-hand side, I have +2. Am I balanced? No, but am I closer?
Yes.
Yes. Right? That means I need to continue to add electrons on the left, that's my right-hand side, to get it to balance. So if I added an extra electron, we'd now be at +1. Okay, still not quite there. I need 3 electrons to get that to completely balance. So let's clean that up. Everybody okay with that? Doing it by yourself is overrated.
Wow.
Copper +2. Copper +2 goes to copper. Same deal, I need to place electrons. Well, I placed them on the right-hand side last time, so let's go ahead and do that. Now what happened?
You went the wrong way.
Right? I did the wrong thing again. I'm at a +2 on the left, and I'm at a -1 on the right. I went the wrong direction. I placed the electrons on the wrong-hand side of the equation, so I'll place the electrons on the other side. Okay? I'm now closer, but am I there yet?
No.
Nope. How many electrons do I need? 2. Now I've got that equation balanced. If we went through and just added those 2 equations together, right? So this is again a moment for not pen. I have an aluminum on the reactant side. I have a copper +2 on the reactant. On a product I have an aluminum +3, and I have a copper. I had 3 electrons on the right, and I have 2 electrons on the left. Just like with algebra, I have the same thing showing up on both sides. I can condense them to one side of the equation. Okay? Which way do I want to condense? To the right-hand side or to the left?
Right.
Okay? I agree the right, but let's screw it up and put it on the left. To condense those values on the left, what do I need to do? How do I get the electrons all on the left-hand side?
Subtract it.
I will subtract both sides by 3 electrons. Right?
So now you have negative.
The result is that on the reactant side, I would have -1 electron, and on the product side, I would have no electrons. Right?
That doesn't make sense.
Can I add a negative thing? No, that doesn't make physical sense. When we're looking at our equations, they're always positive. Okay? That means what I need to do is condense on the left-hand side. How do I do that?
Combining like terms.
How?
Combining like terms.
How do I combine the like term?
Well, you have, well, that's the question.
Subtraction then.
2e,
Minus 2 electrons
right,
and
and then minus,
minus 2 electrons, right?
Yes.
So we've combined our like terms.
so yeah.
Yeah, I did push button. And I would have 1 electron produced. Charges would now balance out, correct? Yes. The issue is I have produced a single electron. I don't know if we did this analysis in the video or last week's class or not. This is saying there's now a free electron just roaming around. Okay? So you're walking through the street and all of a sudden you bump into an electron. Kind of like you're walking through the street and you just happen to accidentally stick a fork in the electrical outlet.
Sure.
That's not going to be pleasant.
Like,
Okay? Do you walk down the street and feel like you've touched an electrical outlet?
not usually.
Probably not. Okay? That's because electrons are highly unstable and can't exist on their own. Okay? That equation is not valid. That overall equation is not valid. I have to go back to the half reactions and I need to change them. Okay? Because of that 1 electron, I need to go back and change these such that when I add, what happens to the electrons? The electrons go to 0. Okay? Notice that when we did this, we had uneven numbers of electrons on both sides of the equation. Okay? So I need to somehow change those equations such that the electrons cancel each other. Okay? Well, can I get half electrons?
No.
Can I get any kind of fractional electron?
No.
No. Okay, so what I need to do is look for the lowest common multiple between 2 and 3. And in the video for last week, we did the same thing, except it was the lowest common multiple between, I know that's stretching, 2 and 1. What is the lowest common multiple between 2 and 1? 2. So we only had to change one equation. At least it appeared that we only changed one equation. But we changed the other equation too. We just multiplied everything there by 1. So what is the lowest common multiple between 2 and 3?
6.
6. How do I make the 3 into a 6? I have to get 2 times that. Well, to get 6 electrons over there, they had to come from somewhere. Where did the original 3 come from? From the aluminum. Well, if I want now twice as many electrons, how many aluminums do I need? Twice as many. Okay? So cool. I'm using twice as many aluminums to produce 6 electrons. But now is the equation balanced?
No.
Because?
You need also the same number for your copper, too.
Nope. Has nothing to do with copper.
Now there's only 1 aluminum on the right side.
On the product side, I now only have 1 aluminum.
So you need the same number of aluminum.
I need the same number of aluminums on both sides of the equation. The way we presented this in the video last week, as I erase half of my stuff, is that we would multiply that top equation by 2. And we go through and multiply the entire thing by 2. What happens? Whoops, bad connection. I get 2 aluminums, 2 aluminum ions, and
6 electrons.
6 electrons. I've only done half of my work because I've only addressed 1/2 reaction. I also have to address the other half reaction. And there, our goal again was to get the electrons to cancel. What is the lowest common multiple between 2 and 6? 3. What do I do to the copper equation?
Times everything by 3.
I need to multiply everything in that equation by 3. 3 times 2 becomes 3 times 1 becomes 3 times 1 becomes 3. So far, so good? What happens if we add our equation up? So we take everything on the reactant side. Okay, for those of you writing this out, yes, this is a bit redundant to write the electrons, but I'm going to do it anyway, because I think you can see the algebra a little bit cleaner. Takes a little bit of time. That was a plus 3. Plus, what are we looking at? 6 electrons. Yeah? Does something show up the same on both sides of the equation?
Yes.
Yes. What is that?
Electrons.
So what can we do?
Kill them both.
I can cancel 6 electrons from both sides. Those disappear from my equation, and I would now have that as my final equation. Is everything still balanced? Well, aluminum and aluminum, how many do I have? 2 and 2. Copper?
3 and 3.
3 and 3. Okay, now the charge, which takes a little bit longer to do than by inspection. I have 3 copper plus 2s. What is the overall charge on the reactant side? 6. On the product side, I have 2 aluminum plus 3s.
6.
Does the charge balance?
Yes.
Yes. What does that mean?
We're fine. Equation's balanced.
Equation's balanced. That could now go with our coefficients into that top expression where we had those lines. Okay, so cool. We've now balanced the overall equation. Did we have to do the half reaction method? No. You could have just gone through and guessed. Well, I think I need 2 aluminums. What happens then? Well, that didn't balance out. So I'm going to try 2 aluminums and 2 coppers. Well, that didn't work. So you could just start throwing numbers at this to try and get it to balance. That sucks. Okay? To put it mildly-ish. Okay? The half reaction method allows us to see the balance of what we're trying to negotiate and get through the process. Okay? To the question that was asked at the very beginning, or for our quiz, how many electrons were transferred? Okay? On a multiple choice exam, you will see 2. You will see 3. You will see 1, 6, and 12. Okay? Why did I pick 3 and 2 as answers? Those show up in the half reaction. Okay? If we look at our complete finalized half reactions, we don't have 2 and 3 anymore. Okay? So if we balance those appropriately, those numbers disappear. Okay? Why did I pick 1? Because 1 is less than 2. That doesn't make any sense to you. It doesn't to me either. I just needed another number. Okay? I then had 6 and 12. How many electrons were transferred? Okay. Well, 6 were produced and 6 were consumed. Well, 6 plus 6 is 12. Melissa, can I get you up for a moment? Mm-hmm. Okay. I have a pen. I'm going to transfer this pen to Melissa. How many pens were transferred?
1.
1. But she accepted 1 and I gave up 1. Isn't that 2?
No.
Okay.
Still 1.
It's still 1. We can't add them across. It's the same electrons being transferred. Aluminum gave up those 6 electrons. Copper plus 2 accepted those 6. There's a 1-for-1 trade, just like trading something between any of you. Make sense? So our final answer is 6 electrons. Okay. A few people had other methods out there for dealing with how you look at those. I have not seen those methods. Okay. When it comes to balancing these kind of questions, these questions show up almost, well, I know for sure, a fact, they show up exclusively in the multiple choice. In which case, it doesn't really matter what work you show, as long as you get the right answer. Right? Unfortunately. So if you have a different method and you can consistently get the right answer, by all means, go ahead and use it. Okay? I don't consistently get it with other methods, that's why I stick to this. Make sense? Okay. So, not a quiz. If we were to predict the product of the complete neutralization of sulfuric acid and potassium hydroxide. Okay? So I want the products. To know this, or to know what the products are, I would have to know what type of equation, or what type of reaction was happening. Do I know the type of reaction right out of the gate? Yeah, I know it's a neutralization. Write in the question. Okay? Because I know that neutralizations produce water, I can immediately say water is a product. Okay? Plus some salt. All right, well, if I'm expected to know both of these, I'm going to have to now move on to the next step, which would be writing out the identity of the reactants to start with. Okay, to do that, what do we need? We need to whip out our awesome another N word. Nomenclature, our naming skills to deal with sulfuric acid. Okay? Because we don't see the hydro, that means we're looking at a ternary acid, which means we'll look at our ending, and the ick came from 8.
I ate too much, so I felt sick.
Okay? And so we end up with sulfate. Sulfate was SO4 minus 2, but I have to replace that charge with hydrogens. I need 2 hydrogens to balance that. Aqueous. Potassium hydroxide. Potassium, everybody knows, starts with P.
No, it's K.
No, it's K. Hydroxide is a complex ion that you're required to know.
Hydrogen and 2 oxygens.
OH with a charge of -1. Potassium a charge of +1. Our charge is balanced. We go through and we do our exchange, the salt. Okay, and that's where this could get a bit tricky. We might say, well, how do we know what that salt is? Okay, well, my argument is that it's not producing water, it's producing HOH. Why does that help us out? I can see the hydrogen and I can see the OH. So what? The first one started with hydrogen. The second one started or ended with OH. What pieces are left over? Potassium and sulfate. They now need to get combined. Which one comes first? The potassium comes first as the metal, and then we drop our sulfate in afterwards. Okay. Did I predict the correct product? Right? To do that, what we have to do is recognize our charges. We could go through and look at HOH. Hydrogen is a +1, OH is a -1. Is that formula correct? Yes. Is our potassium sulfate formula correct? Charge on potassium? A +1, sulfate, a -2. Are our charges balanced? No. To fix that, what do I need? I need 2 potassiums. I have to change the formula. Make sense? Okay. Questions about what you saw there for predicting that? Yeah, Evan.
Isn't it not balanced because there's 2 hydrogens there and only 1 potassium there, and there's...
So there's an interesting question. Is the equation not balanced? Yeah, as you went through, you said there's 2 hydrogens, there's only 1 hydrogen. 1 OH, 1 OH, 1 sulfate, 2 potassiums on the product, only 1 potassium on the reactant. It's not balanced.
But we're not trying to balance it here.
What is the question being asked? Predict the products. Do I care to balance the equation? No. Okay? So it is entirely up to you. If you want to go through and balance every single one, by all means, go ahead and do so. But you can skip that extra work because you weren't being asked that. Make sense?
So the product again was H.
So our products would now be whatever's on the product side. That would be H2O and K2SO4. Questions? Okay. We'll do a balancing one that kind of sucks. Okay. Straight from the quiz. How many people got that question right? I forgot to actually check the last one. Doing the combustion reaction. That was in the online video. I mean, that was a long time ago. So like one person remembers that they got it right. Everybody else got it wrong or doesn't remember? Don't remember. Okay, so let's take a look. How many carbons on the left? 4 carbons on the right. 1. Is that balanced? What do you need to do? This needs to become a 4. Hydrogen's on the left. Hydrogen's on the right. Is that balanced?
No.
That needs to become a 10. How do I make 2 a 10?
Times it by 5.
I have to multiply by 5. Because I'm balancing the equation, I can only change the coefficients. Okay? Oxygens.
2.
On the left, I have 2. On the right, I have
1.
3, 5, 6. They're all wrong. Keep going.
9. No.
There's 2 from CO2, but there's 4 CO2s, so there are 8. There's 1 from water, but there are 5 waters.
So 13.
13 oxygens on the right-hand side. Everybody see that?
Oh boy.
Okay. So from CO2, how many oxygens are present? Just CO2. There's 2 oxygens, but I have 4 CO2s. That coefficient applies to everything afterwards. So I have 8 CO2 or 8 oxygen atoms in the equation, which would be our 8.
Why do we have 4?
Why do I have 4 what?
CO2s.
Okay. Why did I need 4 CO2s?
Carbon.
Oh, because they're on this.
To balance out the carbons. So we started with our carbon. We had 4 carbons on the left.
So you had to make it.
We had to make a 4 there, so we had the 4 carbons to balance. Are we caught up? Okay. So now the real fun question, how do you make 2 equal to 13?
Multiply them together and make 26.
Okay. We can multiply them together and make 26. Okay. That'd be fun. And it's unfortunately probably the best bet. Okay.
Sorry.
Which means we'll make this one a 13.
Oh boy.
And now we run into a fun issue on the other side. Or actually, yeah, we kind of do. What do I need to do to get that 13 equal to 26?
Times everything by 2.
Times everything by 2. I can't selectively multiply one of those by 2. I have to multiply them both by 2. So that 4 becomes an 8.
Which makes carbon not balanced.
We'll come back to that. That makes that 5 a 10. Okay. We changed numbers, which means
Start over.
you have to go back and check your work. Oh my God, yes, that's exactly the response I want out of this. Okay, believe it or not. Carbons on the left. 4 carbons on the right. Are those balanced?
No.
What do you need?
Times it by 2.
To put a 2 there to make that now 8. How many hydrogens do we have on the left?
20.
We have 10, but 2 of those molecules, so we have 20 on the left. How many do we have on the right?
20.
Ooh, there's 2 from H2O, but I have 10 of those. 20. Hydrogen came out balanced. Oxygen.
26.
2, 13 of them. That's 26. We have, that 4 is bothering me. Sorry, I need to erase that. Okay, we have 2 from our CO2, but 8 of them, so that's now 16 plus 10, and I have 26. We changed a number, so you check it again. Okay? You will find that it is now balanced. Okay? Usually a good check just to make sure. Could we make those numbers smaller? Well, we would find the smallest number in it, 10, 8, 13, or 2. 2. Are all of my coefficients divisible by 2? 13 does not divide. divide by 2. So I'm at my smallest whole number values. For the sake of the question on the question that's actually up there, right? What is the sum of the coefficients when balanced? 2 plus 13 is 15. 8 plus 10, 18. 5 and 8. That's why I use a calculator.
23 plus 10 is 33.
I'll accept that. 33, and your answer becomes 33. Yep. Do all combustion reactions require this melee of multiplying and dividing and all that? No. No. It only comes out if you hit a half value or hit an odd number of oxygen atoms. When you hit an odd number of oxygen atoms, that's where you're going to have to deal with this multiplying through. And yes, it sucks, but you have the method. Make the numbers the same, however, in any way you can.
Is that why when balancing, oxygen is always kind of the last thing you do?
Why do we save oxygen for the last? For this very reason. Oxygen shows up in too many locations. We don't want to have to start with oxygen and then have to go back through because it messed everything else up. Okay? Our hope is that oxygen solves itself. Take heart. You only have to worry about the exam Wednesday.
And then the final.
Yeah. Right. So now some just kind of general fact stuff. Conservation of mass. You can't create or destroy matter. Right? Doesn't happen. Right? So if we start with matter, we must end with that matter. We did this when balancing equations. Right? We can also do it in, say, a combination reaction. If I start with, and please, for those of you at home that know all the math, don't mock my math on this, which won't be obvious to the rest of us if we don't know it. If I start with 2 grams of hydrogen and 8 grams of oxygen, how much water do I produce? Let's avoid sig figs.
Because you need liters.
Nope. I can measure any mass, any volume, doesn't matter. I don't need liters.
But you mix 4 grams of water.
2 grams of water, 8 grams, or 2 grams of hydrogen, 8 grams of oxygen. How much water do I make?
4.
Conservation of mass. I cannot destroy matter.
So 10.
If I can't destroy matter, the mass I start with must be the mass I end with. We'd have to get 10 grams. Okay? So all we have to do is add. Okay? And it seems straightforward and easy enough. Okay? But there are cases where this becomes problematic. For instance, let's take a look at wood and oxygen. Let's take 100 grams of wood, 2 grams of oxygen. How much gas do I make?
Some amount.
Some amount's not a bad idea. I heard 102.
You make X.
I make 102 grams of
Gas and water.
gas and water.
So you make X and Y.
What did I make of the gas?
X.
Whatever burned off the wood.
Water also burned off the wood. Okay? It's unsolvable at this stage. Using just the conservation of mass, we can't predict the amount of gas or the amount of water individually. Because we don't know that when we burned wood and oxygen, how much gas was produced, how much water was produced, as far as their amounts. Right? We literally don't know that information. All I know is that the total product amount is 102. But what if I go through and tell you
50-50.
that water was produced as 62 grams?
Well, then you minus 62 by
40 grams
102, and then
of
you
gas.
have...
Right. I now know that the gas is composed, or is whatever's left over from 102. What color do I have? Minus the water of 62. The gas is now 40 grams.
Yes, I did.
Make sense? So our conservation of mass works great for combination and decomposition reactions. Why those two reactions and none of the others?
Because those are the only ones where you have one product.
The combination and the decomposition are the only reactions that either produce only one product or start with only one reactant. And as long as you're solving for the one piece, you're okay. The instant you have to solve for a split, you can't use conservation of mass anymore. We'd have to use something else. That something else involves balanced chemical reactions. Notice I intentionally buried or took formulas out of this so you couldn't balance them. Okay? Einstein came along and said energy and mass are related to each other, which means if I can't destroy matter as mass, I also can't destroy energy. Okay? We can convert it from one location or one substance to another, okay, or one type of energy to another, but I can't destroy it. Okay? So I have the total mass and total energy in our universe is constant. It never changes. Okay? Back to our conservation of energy. It can be converted from one form or another. So what are the forms of energy? Heat. Light. Electricity. Nuclear. Did pretty well. You guys skipped like the biggest one. Come on. Chemical. Okay. Those are our 6 primary forms of energy, and we can jump back and forth between these, usually with the production of heat as a byproduct. Heat is the one that accounts for why we run out of energy, okay? Because heat is something we can't control quite as efficiently as any of the others. So how do we get light in this room? Electricity. Where do we get the electrical energy from? The power plant. Where did the power plant get the electricity from?
Water.
Generating it. How?
Mechanically.
Okay. Mechanically, sort of. We have nuclear and nuclear power plants. Right? How do we get the mechanical aspect of our generators to work? We used nuclear power. What did we use the nuclear power to do? To boil water. Steam turns the mechanical energy, or turns the turbines of our mechanical energy to generate electrical energy. The electrical energy gets pumped here, where we can then convert it into light. Okay? So you've got a sequence of several steps on the process of trying to get that electrical energy. What happens at each of those stages? We produce heat, which is then lost. So every step we take to get this light energy reduces the amount of energy production, or the amount of energy that we need, or can access, rather.
What's the most efficient?
What's the most efficient?
Nuclear.
Start with light. You can't start with light.
Sure you can.
Walk outside. Okay?
Well,
Our most efficient use of energy is to use the energy that is immediately available to us. Instead of going inside, we should be outside where we have light. Right? So we don't have to use lights.
Isn't that
Right?
still heat, though?
In our house, we could use skylights to light our rooms. Right? What becomes an issue with that source of energy?
Sun disappears.
Nighttime. Okay, nighttime, that source of energy disappears, and we would need an alternate source. Right? It's now looking at the rest of those and deciding which of those alternate sources is best for us. And yes, being in Arizona, we are acutely aware that using the light energy outside is not always the best, because
It kills us.
that light energy is also associated with
Yeah.
heat energy, which then cooks us, which isn't particularly fun.
If only there was a way to store it.
If only we had a storage mechanism like batteries, okay? Which, believe it or not, comes back to
Chemicals.
chemical.
Which is why
Right.
you don't need batteries.
Finding chemicals that can appropriately store that electrical energy. That's batteries.
Is that like solar panels?
I mean,
Solar panels
consider
trap it, okay? They trap and convert that light energy into electrical energy directly. They aren't
but it
actually
is
storing it.
like a chemical reaction because it's like batteries, right?
Somewhat.
Not quite. We can talk
Unless you
about that
have
in a little bit more depth later, but it's not quite. It's going to come down to your definition of chemical. Okay? Where is our current battery storage? Battery in quotation marks.
Bunny. The energizer bunny.
So we can talk about where we've seen batteries, like lithium, right? The alkaline batteries. I would argue that we have our most common storage of energy, our chemical store of energy as a battery is fossil fuels. Fossil fuels are a battery. They're a way to store energy. To get access to that energy, we also have to release a bunch of other byproducts, and we hope to minimize that, but even normal batteries still have byproducts, because eventually what happens to the battery?
It explodes.
It dies. It no longer holds its charge, which can be catastrophic. Okay? So it's coming up with a way to store that energy that also doesn't release a bunch of other things, and that becomes problematic, and how we decide to do that. Okay? So mechanical energy tends to be the most common one. We could look at cannonballs. If you've taken a physics class, they usually calculate, or have you calculate, how far does a cannonball go if it has X acceleration and Y distance and all that fun stuff. Okay? To get the cannonball to even move, to be able to do a physics course, you had to have gunpowder, which was chemicals. And it's the energy stored in those chemicals that are now causing a rapid release of gas to force the cannonball out. Okay? If we look at a combustion engine, okay, our combustion engines with our cylinders and pistons are doing the same thing as the cannonball. Okay? When you turn on your car and step on the gas, you are firing cannonballs. You're just firing them very small distances and controlling that motion to convert it into rotational energy, which then converts into translational energy, moving your car forward. Okay? All of that comes from a chemical reaction. Okay? If we look at the far right, ATP and ADP, okay, then we got some structures shown with those. Anybody know what those are?
Lewis structures.
Yeah, Lewis structures. What did you get in the back? ATP is our energy storer for muscles. Right? It's how muscles function. Okay? We talked, I think, maybe I just talked with one person, about sodium and potassium ions moving across membranes to get our muscles to work. They don't move freely on their own. They need to be pushed by ATP. ATP is providing the energy to allow the ions to move back and forth, which is allowing us to contract. And what's the opposite of contract? Extend?
Yeah.
Extend our muscles. Okay? I thought there was a fancier word. So it all comes back to ATP. What's changing when we go from ATP to ADP? So you see water. A T is changing. What does the T stand for? Tri. What does the D stand for? Di.
So we're losing one phosphate?
We're losing one phosphate. You look at the structures, the only thing that has changed is that you removed this one tiny little group. You moved a phosphorus and 3 oxygens, and that is enough to drive nearly every chemical reaction in your body.
Nice.
What? Yeah. Pretty impressive. What if you tried to remove more of those?
You die.
You would probably be producing enough energy that, yes, you would probably die. Okay? So it's kind of neat to look at how the body consumes the energy and how it processes it. It all comes back to chemical energy. Okay? Kinetic energy in physical states. Okay? So if we look at a given temperature, what phase has the most kinetic energy? Well, what is kinetic energy? Motion. Okay? Kinesiology is the study of the human body moving, right? Any kinesiologists can help me out? Yeah, close enough. Okay? It's how our human body moves. So kinetic energy is now just the energy associated with movement. That's it. So which of our phases at a given temperature, and we have to keep that constant when we evaluate this, has the most kinetic energy?
Salt.
Gases. They're the ones that are moving the most. Okay? At room temperature, how much is this table moving? Not a whole lot.
A
Right?
little bit.
But the air that we're breathing is constantly moving throughout the room. Right? So kinetic energy in our gases is the highest. Right? Does that make sense to how they're structured? Well, if they're constantly moving, how likely are they going to be confined next to another element? Not really likely. If we look at the solids, they don't have any energy, which means they're all going to just settle at one point and all collect next to each other. Okay? So we can evaluate that energy back to our general phases. Right? What happens if I increase the kinetic energy? That's not quite what I meant to say. Let's read the question appropriately. What happens to our kinetic energy when we increase the temperature?
We should get more kinetic energy.
We should have more motion. Okay? If we increase the temperature on ice, what happens to it? It melts and turns into, give me a phase, a liquid. Do liquids have more kinetic energy than solids?
Yes.
Yeah.
Unless it's really hot.
So all the way shifting through, and if we add even more heat, we move all the way up to the gas, and even then, what happens? We have even more kinetic energy. Okay?
But doesn't the kinetic energy stop at one point if the temperature goes above a certain place, or does it just keep increasing?
Our kinetic energy will continue to increase. Yep.
Okay.
Until it just doesn't stay together.
Yeah, until we get ultimate destruction. Yeah. Do all phases have energy?
Yeah.
All
A little
phases
bit.
have energy, but not
A little
This question gets a little bit weird. Because when we look at the table, is it moving?
Technically no, but technically yes.
Not that we can see. Every atom, every electron, every proton within this table is moving. It's just moving at a frequency we can't detect. Okay? With our eyes. So when we're asked the question, do all phases have kinetic energy? Yes, they all do. Okay? Some just have incredibly low energies that we can't physically see.
But we also can't physically see gas energy either.
That's a good point. Our gases that have the most kinetic energy, we don't see them either.
You just
Right.
don't see kinetic.
So we have to make that parallel and recognize
Kinetic energy when it's a liquid.
that our energy can have varying states. The gases have the highest kinetic energy, the solids have the lowest. Are there other phases? Yeah. We've got plasmas, which tends to be the most common one that students have heard of. There's also varying stages of solids. So not just a solid, but we can have solids at different levels of solid, believe it or not. Ice tends, or H2O tends to be one of those kind of compounds. Yeah.
Could you mix all of them together?
So all of them, yes and no. Okay. Of the three standard phases, solid, liquid, and gas, yes, you can have all three phases in existence at the exact same time. Right. That is known as the triple point because it is the point at which we have three different phases.
Is that like fog?
That's our triple point. Not fog. Fog is going to be two phases, liquid and gas. Right. The triple point, you can watch videos or find videos online. In fact, I'm pretty positive that I've got a video on it in one of the online videos that I don't think I required you to watch. Right? But you can get the triple point. The easiest one to hit the triple point on, though somewhat dangerous, is dry ice. If you have a secure enough clear container, you can put dry ice into that clear container and cap it. What happens to the solid? Becomes a gas. It's called dry ice, meaning we typically don't see the liquid state. CO2, or dry ice, typically goes from a solid directly to the gas. It sublimes. Right? With our conditions of hitting the triple point, there's two features we have to nail down. It's temperature and pressure. Both of those aspects are important in hitting the triple point. So what happens when we've got our container with the dry ice inside it? It starts to build up pressure. So as the pressure changes, that's what's going to help us hit the triple point. And if we're lucky and have the proper pressure and temperature, you will see all three phases of CO2, solid, liquid, and gas. Right? The massive issue with this, which is also the other part of this, I'm by no means telling you to do this, right? Because you've probably heard of dry ice bombs, right? Right? Dry ice bombs involve taking dry ice and other things.
Soda can, cigarette strap, duct tape, drop it.
I can neither confirm nor deny that.
Design. Neither
The,
nor design.
the issue with those is that you have a closed container with a rapidly expanding gas. Closed containers with rapidly expanding gases are known as bombs. Okay? So you have to have a container that will withstand that pressure, otherwise it does explode. Okay? And that's not a particularly fun experience to be around. Okay? But it is neat. Okay? So yes, you can achieve the triple point. Dry ice is probably the easiest. But again, you've got that pressure differential that becomes difficult.
Another question, where would we see plasma?
How do we get to a plasma? A plasma is at such high temperature and pressure that we no longer have a liquid or a gas, that it crosses over and it's a blend of both of those phases.
Every star everywhere?
Yes, I believe they are plasmas. Yeah.
I think so.
Energy and chemical changes. If we have water, I can convert that into hydrogen gas and oxygen gas in what type of reaction? Now you're like, oh, you didn't ask any questions. We don't have to pay attention. Whoops. Start with water, and I end with hydrogen gas and oxygen gas. It's a decomposition. I'm starting with one thing and ending with two. I can force that decomposition to make hydrogen gas and oxygen gas. Okay? I can then take those two things and add a little bit of spark to initiate a reaction, and then they would rapidly explode, okay, to produce water again. So if I put energy into water, I can cause it to split into hydrogen and oxygen. Okay? Hydrogen fuel cells, everybody, that technology floated out there for a while. Oh yeah, hydrogen's the next big thing. Okay, we'll use hydrogen fuel cells. And go, oh, it's so much cleaner. All you do is produce water. How did you make the hydrogen gas? From oil. You're only adding an extra step to the process of getting that translational energy. You're only producing a bigger loss of energy with hydrogen fuel cells. Okay? They don't have the technology yet if we're going to deal with oil as our ultimate production of that energy.
Can we just use a chemical spark?
It's not the spark, it's the actual energy. To split water into hydrogen and oxygen, you have to add a lot of energy. Okay? To get it to go the other way, that one's a lot easier. That all you need is a spark, and yeah, that will ignite and very quickly produce water. Okay? And it will self-sustain. Okay? So I thought this question was a little fun, so we figured I'd go ahead and throw it in here. When we drop the temperature, we move from a gas to a liquid. Okay? So if we think about, everyday uses, filling up our gas tank, right? If we filled it up with gas, okay, it's going to build up so much pressure that we're not going to get a lot of gas in there. So we tend to use as our storage for our gas a liquid phase. So we don't drive around on propane tanks, we drive around with octane, which has a higher boiling point, which means it stays a liquid. Okay? What happens is I add heat to the liquid.
It expands.
It expands. It has more kinetic energy. It will move. It can still stay a liquid, right? I can have water at 10 degrees Celsius and at 90 degrees Celsius. They're still both water. But the 90 degrees Celsius one has more kinetic energy. The more it moves, the more volume it takes up.
Does that mean that oxygen is being put into it? Is
Nope.
that what
Nope.
makes that?
Nope. It's just more energy, heat. Right? So if we think to our gas tank now, when we go to the gas station and we fill up our tank with gas, how is it getting measured?
Liquid volume.
By volume, not by mass. Right? Which means if our gas is moving more, what happens to the volume?
It's less. No, it's the same.
Volume increases.
The volume will increase. It's moving more. Right? If I don't move, I take up a relatively small amount of volume. But if I start moving, that's going to get a little bit more volume occupied because I'm now taking up multiple spaces. So what does that mean for our gas tank? If I now want to go fill up my gas, do I want it to be cold gas or hot gas? Cold, because if it's cold, it's not moving as much, which means it takes up less volume, I get more mass, and it's the mass of the gas that is actually combusting. It is those chemicals that are generating energy. So if I can get a larger mass in, I'm better off.
But we're paying for the volume.
But we pay for the volume. Right? Which means it is best to fill your car when it is cold outside. Filling it up in the afternoon is then a bad idea because now the gas is hotter, which then means you're paying for less gas but the same price. Okay? So you end up paying a little bit more. That kind of sucks. Right? So we should all, as our lesson from this, go home and only fill our car in the middle of the night when it's the coldest, which is somewhere like 3 or 4 in the morning.
I don't think it really matters that much.
Doesn't really matter at all that much. Believe it or not, that's true. It doesn't. The density change between the coldest temperature that we get, at least in Arizona, and the hottest temperature we get in Arizona is virtually nothing. Right? Which means what you are saving is probably hundredths of a penny per fill-up. You are saving money, don't get me wrong.
But it's not.
But probably in your lifetime you will have saved a dime. You are better served by just picking up spare change off the ground. Okay? So, with that, we have 15 minutes left in class. Right? This would be your time to ask questions. So the rule of 7, which I have never heard of, is the same thing as the have no fear of ice cold beer. That's your diatomic elements as best I can tell. What question number was that? Question 12 from the practice exam. Ask a question about diatomics. Yeah. Rule of 7 is the same thing as have no fear of ice cold beer. Okay. I think I will have a really hard time scanning back through it. But let's see. Come on. That would be... That would be this slide, the rule of 7. So we have the 7 for our diatomic, but there's only 6 highlighted on the far right. That's because you also have to include hydrogen. So yeah, apparently that's called the rule of 7. I'm okay with that. What's that? Okay, yeah, that's cool. Question. 23. Okay. Actually, can you open that again? Real quickly, attempt to draw something here. This may look absolutely ugly and awful, but it's pretty close to what's on the practice exam, so it should help out. So I give this structure and make sure I'm pointing to the right spot. Point to that oxygen and I go, oh my gosh, what does the oxidation say to that oxygen? 9 times out of 10, everybody looks at it and goes, holy crap, there's no way I could ever answer that question. I've never even looked at that structure before. Here's what you need to answer this question. And this is going to be kind of annoying. Sorry. I'm not sorry. But here's what you need to answer the question for the oxidation state of that oxygen. Everything disappeared.
The oxidation state for any oxygen.
-2.
Oxidation for any oxygen is -2. Doesn't matter where it shows up, it's -2. The structure is there only to make you panic and think something else is going on. The oxidation state for oxygen is -2. -2.
Please tell me that show your work.
Yeah.
Show your work.
It's the whole symmetrical thing with the polar and non-polar being reliable.
So This question is really lab-based because we didn't talk about it in lecture and it won't show up on the exam, but just in case. Polar versus non-polar, there was a question about symmetry. If it's symmetric, it's non-polar. If it's not symmetric, it's polar. Reliable enough. Reliable enough. So if you have a non-symmetric structure, it is, non-symmetric is polar. If you have a symmetric structure, it's non-polar.
So basically, if you have unshared electrons, then that is non-polar.
That is symmetric and non-polar. This one is
Polar.
That is polar.
polar and not symmetric. The not symmetric and symmetric thing is a bit of a challenge here because technically that structure is symmetric, but it's at what levels?
But
Okay.
it's not
So
shared.
completely symmetric is non-polar. Varying levels of symmetry typically are polar.
So things that look like they should be polar are not polar.
That one looks like it should be polar, right?
No.
Oh, it doesn't? Oh, okay.
I remember it by if there is a set of electrons that are not being shared. Yeah.
So the cheat is we take a piece of paper, put your center atom in the middle of that, okay? Because everything we're doing in 130 has at most 4 electron groups. So we have 4 corners on our paper, right? Okay. So now the question is applying your shape appropriately. But once you have the shape set up, you can now apply it to the piece of paper. Okay. So if we had CH4, there were 4 groups, which means each of those corners is a hydrogen, and the center is a carbon, right? Okay. Well, there's a difference in electronegativity, so each of those hydrogens is going to pull on the electrons. Technically the other way, but okay. Let's say it's going to pull on it. I only have 2 hands, so unless you can help me out. Okay. And so now what we're going to do is we're going to pull on those corners. You can pull. Come on. Okay. You can still pull. Come on. You can do better now. There we go. Don't change your pulling. Just pull. Pull harder. Okay. And what happens to the center?
It tightens.
It stays the same. It didn't move. What happens if we went to NH3? Are you still pulling?
Mm-hmm.
Okay. What happens if we go to NH3?
Apparently NH2.
The center atom moves a little bit because there's now nothing counterpulling here.
Gotcha.
There's nothing countering these 2 pulling away. The result is the center atom moves, and we now have a polar molecule. Right. Really bad argument as far as spatial awareness and all that goes, but it gets the problem solved for this class. Right. So if you have questions more about that in that demonstration, I can talk through it a little bit after class, but it isn't that big of a deal for this class. Other questions? Yeah. Ooh, wow. A mole one. Oh my gosh. Do I know anything about moles? I didn't say anything about moles, did I? Yeah, so some people could go through and spit it out. You read about moles?
That was 10.1.
What?
Yeah, 10.1 was the other day. 10.1 and 9.1 and
No! Ignore all that! Crap.
So does that mean we don't have to do a reading assignment next week?
You should not have been reading about moles. I apologize. That should have been right after the exam. That was the reading supposed to be for next Monday. Well, I apologize for that. Regardless, you do not need to know anything about moles. So, which is kind of weird because this question has stuff about moles. And you'd be like, well, Mike, you just said I'm not supposed to know anything about moles. That's true, you're not. But you can still answer this question without having a single concept of what moles are. This is short answer E.
So moles are not on the test.
Moles are not on the test. Yeah. You want to say that louder, Paul?
It's inconsequential as to the question. You can replace mole with Snorlax.
I can replace those units with anything I want.
Right.
Completely irrelevant to the question. But what was the question? The amount of water?
Yeah.
Okay, so we set this up. I want to know the grams of water. Okay, so what do? Convert.
Version.
Right? I got 3 conversions. Where do I start?
What are you trying to get?
Okay, the one I know. Which of those do I know? Which conversion? One, we'll number these. We'll call this A, B, C, D. Which of those do I know anything about?
A.
Okay. Mole H2O, mole of H2O. It does, I agree, that has H2O, but does it have grams?
No.
No, so I don't think A is going to be super useful.
Let's go with
9 grams
B.
equals O2.
We have grams and O2 in B.
B, grams and O2. So I have grams, but I have O2. What do I have for my answer?
No, hydrogen.
H2O. That's still not the same thing.
D.
D.
Okay, D. What does D have?
Grams and H.
Grams and H2O. Okay, so let's go ahead and stick with that. Okay? And I'm going to start going from the right left. Probably just telling you that you can leave class. I want grams of H2O on top. Why?
Because it's what we want.
That's where it shows up in our answer. And I want moles of H2O on the bottom. What number shows up in front of grams of H2O? 18.0. What number shows up in front of moles of H2O?
1.00.
Yeah, fair enough. I'm not going to deal with sig figs. That was conversion factor D.
Always deal with sig figs.
Yeah, I know. So cool, I now have what I want for an answer. Grams of H2O, grams of H2O. But I also introduced
Moles.
moles of H2O. Do I want moles of H2O?
No.
So what do I have to do?
Cancel mole.
We want moles H2O on top. Yeah.
Right?
Kill the mole.
Where do I have moles of H2O in my other conversions?
Everywhere else. A.
A. So let's go ahead and use A. Where is it? That's, whoops.
O2.
Moles of O2. It said 2 moles of H2O, 1 mole of O2. That was conversion factor A, right?
Yep, now we need to use C.
So cool, I got rid of moles of H2O, but
Now you have mole of O2.
now I have mole of O2. So
Cancel out mole of O2, which is C. Use B.
B has grams of O2.
Ah, crap.
Nope, we need C.
We need to use C that has moles of O2.
There you go.
I would say thank you, but it wasn't me that told you that.
You have 1 mole of O2. and 16.
So we have 1 mole, 16 grams. Yeah?
Now we can cancel out the grams with B.
But this meant that I now brought in grams of O2. Do I want grams of O2? No, so what do I need to do?
That's B.
I need to bring in grams of O2. Am I given grams of O2 somewhere?
Yes, 9 grams of O2.
Yeah, B just says 9 grams of O2.
Oh, that was exciting.
Over 1.
Okay? And then if it makes you feel better, you can put it over 1. What happens? Grams O2 cancels. What unit would you be left with? Grams of H2O. Do you need to know anything about moles?
No.
No. Okay. This question is kind of tricky because everybody freaks out because people have this concept of moles being associated with chemistry and go, oh, as soon as I see moles, everything just kind of glazes over and disappears. You don't have to know anything about moles if you paid attention to how we solve questions. This is our dimensional analysis setup. It removes our necessity to understand what it means. And yes, that may seem like a horrible thing for a teacher to tell you, but that's because once you can do the calculations, then we can spend time in understanding the meaning. Right? But I want to get through the calculations so we aren't fighting on both the meaning and the calculations. Calculations, once you set it up, you just go through and solve. Will you see this question again?
Yes.
Yes. You will see it again on the next, in the next unit. Right? And just to give you kind of a little bit of a preview on what's going to happen in the next unit, the only thing that you will be given will be that. Yeah, how could you possibly solve that? Because every other conversion factor I gave you is already known to you, you just haven't realized it yet. Admittedly, I made a typo in what I gave you, but beside the point. Okay? The next unit is finding those conversion factors, is knowing where they are. It's then just a question of plugging them in into our system, and we're good to run. Okay? With that, we got to end. I will be in office hours right after class, but a little bit later. What's that? I should be in tutoring tomorrow.